In this example, we want to test a claim about a mean when sigma, the population standard deviation, is known. A simple random sample of 40 receipts from a grocery store has a mean of $137. 2 years ago, a similar study of the grocery store was conducted, and the mean from that study was $131. Assuming a population standard deviation of $30.20, test the claim that the mean sales of the grocery store is increasing. So what would it mean for it to be increasing? It would mean that it is more than $131, more than it was 2 years ago. And we're to use a 0.05 significance level. Okay. So we were given the population standard deviation. I'm just going to make a note of that over here. 30/20 or 30.2 is what I can enter in the calculator. And now we want to determine what the original claim was. So the original claim is the mean is increasing more than 131, more than $131. So what competes with that, what covers everything else, is that the mean is less than or equal to $131. Okay, null hypothesis, always equal. The mean is $131. The alternate hypothesis, and this is where this analysis helps us, so the condition of equality is with the competing claim, so they're corresponding, so that means that the original claim corresponds to the alternate hypothesis, mu greater than $131. And I want to make a note up here, our alpha is 0.05. Okay, so we will find our critical value. The calculator will give us our test statistic and our p-value. And we'll make a decision. So now let's look at our decision diagram. This is the z distribution because sigma is known and my mean is always 0, and I look up here at the alternate hypothesis. This tells me what type of test I have. It's a greater than symbol, it's pointing to the right, so I have a right-tailed test. And this represents, let's see, get another color here. Here's my alpha, which is 0.05. So now I can get the critical value using inverse norm, area to the left. Well, if this is 0.05, then to the left is 0.95. Okay. So we go to second to our distributions, tab down to inverse norm. I'm going to enter 0.95, enter 1.6448, and this is that common one that is often written to 3 decimal places, 1.645. Okay, so I'll write that here. My z is 1.645, and down here. Again, we got a positive number, makes sense, it's on the right. Okay, now we're ready to enter this into our calculator to get our test statistic and our p-value. So we say stat tests, and for the mean, the hypothesis test of the mean, when sigma is known, we use the z-test. Recall that when we were finding the confidence interval estimate for the mean and sigma was known, it was the z-interval. And now we're doing a hypothesis test, so it's Z test. Okay, just like with confidence interval estimates, it will give me an opportunity to indicate that I have the raw data in a list in my calculator, or I just have these sample statistics, and that's what I have, just the sample statistics. So I'll highlight stats. Tab down. What's the mean? Mu with this subscript O means what's your null hypothesis value? That's the 131. My sigma we said was 30.2. The mean from the sample was 137, and my sample size was 40. And now we need to indicate what the alternate hypothesis was, or what kind of test did we have. And it's the right-tailed test. Highlight the right-tailed test, and now we're ready to calculate. So we see we get a test statistic of 1.256. Rounding z-scores usually to 2 decimal places, I'll say that's 1.26. And the p-value probabilities to 4.10446 would round to 0.1045. Okay, so my test statistic, change colors, and we said that's a z of 1.26 and my p-value of 0.1045. Okay, so let's get the test statistic on here. 1.26 would be somewhere around here. Okay, so note that this area represents the p-value. Okay, and so clearly looking at the two methods, does the test statistic fall in the critical region? No, it does not. So that means we would fail to reject HO. Now let's look at the p-value decision. Is the p-value less than alpha? Is 0.10 less than 0.05? No, it is not. We can see the area for the p-value is larger than the area for alpha. So both of those lead us to the decision that we fail to reject the null hypothesis. Okay, so the only thing left now is to write our conclusion. And remember that how we word that depends on, first, does the original claim contain the condition of equality? In other words, does it correspond to the null hypothesis? Because if it does, our decision about HO is the same decision for the claim. But no, it does not. They do not correspond. So the answer to that's no. And then, did you reject the null hypothesis? Well, the answer to that is also no. So our conclusion: there is not sufficient sample evidence to support the claim. And this is where we just look back at what the claim was, that the mean sales of the grocery store is increasing. Okay, and this word sample, you can put that or not put that as sufficient evidence. It is sample evidence. That's what we're using for our evidence. It's just a little more specific, but you could also say there's not sufficient evidence to support the claim that the mean sales of the grocery store is increasing. So let's go back up here again and note this conclusion and why we say what we say. We failed to reject HO. So in other words, we have no reason to reject HO, and HO corresponds to the competing claim, not the claim. So in other words, if we can't reject this, then we don't have any support for the original claim. And that's the way to think about it. And then even further back, thinking about what had happened here. So 2 years ago, they had a mean receipts of $131, and now it's $137. The question we're asking is that difference statistically significant? That $6 difference, does that give us reason to believe that sales are going up? It's a larger number, but is it statistically significant? And that's what a hypothesis test helps us determine. And what we found was, well, based on that sample, no, it's not, and we don't have the evidence to say that it's increasing.